All right, guys. Welcome to the week 4 discussion board. Today we'll be talking about fitting a multivariate curve. The discussion board team leaders were me, Chris Kontos, and my teammate Uriah Lerner. He worked on the majority of the PowerPoint. He did a great job. We are going to present this thing right now for you guys. Here we go. So question 1. Question 1 is going to ask us. Let me pull it up. Question 1, we got, using what you know about multivariate linear functions, do your best to estimate a linear function for this data. Answers will vary. Yes, it will be rough in the sense that the slopes are not constant, but make some judgment calls and decides on slopes in either directions. After that, he wants to know, what do your slopes and your intercepts mean in practical terms. Alright guys, so let's look at this table. We've got all of our numbers, and we want to put this in a linear regression in the form z equals mx plus ny plus b. Alright, so moving on, what we want to start out is by estimating our m and our n values. These values up here, we got our m, we have our n, and then that's our b intercept right there. So we want to start by assigning variables for these letters essentially. So let's suppose that across the top is our x values. So we got 5,000 is our x, 6,000, 7,000, 8,000, 9,000. Perfect. And then our months are our y values, 12, 24, 36, 48, and 60 months respectively. Since these numbers are not linear, we won't get an exact solution. You could just tell by looking at this graph. You could tell by looking down, looking sideways. It's not exactly perfect. So we're gonna get a nice estimate with these numbers and with these slopes. Pretty much we're looking for that closest fit. So to do this, let's find our average change in x for the whole table and our average change in y for the whole table. Alright guys, so we're going to start by finding our m, which is going to be our change in x. That slope for in the x direction. We're going to start by subtracting each of the right numbers from the left numbers. So we're going to subtract that 9,000 from the 8,000, the change in x, and then for the change in z, we're going to subtract that 1,000 from that 900. And we're pretty much going to do that for each row. So we're going to keep that y constant for the differences that we do, and we're going to do that for each. We notice that going along the x-axis, it does seem to grow linearly for each row. So just by observation, you can see that going from here to here, and from here to here, and from here to here, and from here to here is all going to be the same. So for each row, we find the differences. We get our 112.83 for that top row, 72.48 for that second row, 60.44 for that third, 55 for that fourth, and 52 fifth. So what we're going to do with those numbers is we're going to take the average of them. And what we find is that we get roughly 70.7 for our change in z. So all these numbers represent our z values, and that average amongst all these numbers for our change in the x direction, so from here to here, or here to here, or here to here, that average is going to be 70.7. Next, we can get m by taking our change in z and dividing it by our change in x, as we can see from up here. Change in z, change in x. So we know our change in x is 1,000 because we could see 5,000 to 6,000, 6,000 to 7,000, so on. We can plug these numbers into our formula for m, and that will equal 70.7 for our change in z over 1,000, our change in x, and that is around 0.07. So you'll see that pop up right here, and this should change throughout the PowerPoint, so keep an eye on it just to keep track of where you are. So next we're going to be finding our n value. Our n is going to equal the change in z over the change in y. So now we're going to be looking up and down. We're going to be looking at the jump from here to here. We're going to jump from here to here, and maybe jumps from here to here, jumps from here to here. We have to look at all the entire table to get that most accurate fit. So this time, the numbers do not grow linearly, so we have to average each individual change instead of averaging the rows. So instead of just doing the entire row, since the row does change, because we have a decrease of what we got, like somewhat like a 200 decrease, and then we got like a $60 decrease, and then even less than that, and then even less than that. So it's kind of difficult. That is definitely not linear from just looking at it straight up. So what we're gonna have to do a little bit of work with this one. We're gonna have to find the average of all the changes, and after doing some work, crunching some numbers, we found that the change in z happens to be negative 105. So the average across all these is going to be a change in negative $105. The next, to get n, that should be an n, by taking our change in z and dividing it by our change in y. So we're going to take our change in z, that negative 105 that we found, dividing it by our change in y, which is going to be that 12 to 24, which is 12, 24, 36, that's 12. So pretty safe to say that our change in y is going to be equal to 12. We could plug these numbers into the formula for n, so that's going to equal negative 105 over 12, giving us that negative 8.75 slope in the y direction. So you see that pop up there. Now we're going to be looking for our b-intercept. The b-intercept is pretty straightforward. We just need to take the median value of the table and plug that into our formula. You could use any other value on the table. We just chose to use the median just because that gives us the pretty much the middle ground for what that intercept could possibly be. Because if you, with a nonlinear table that we are inferring it being, you never know what you're going to get with those oddball numbers in the corners or just on the outskirts. You kind of want to get that central number. So we went with 7,036 or 2304 as our value to find that b. When we plug those numbers in, we get 423.04 equals 0.07 times 7,000 minus 8.75 times 36. You want to make sure that you're putting those values in the correct spot. You do not want to switch that 7,000 and that 36. That could throw off your entire thing, get you a crazy intercept, and all of a sudden you're making payments you don't want to be making. So that new value is 248.04 for our b when we isolate it and we solve for it. This gives us a new formula of this right here, 0.07x minus 8.75y plus that 248.04. Now obviously not everybody is going to have the same equation. It's really up to how you processed the table, how you came up with your numbers, but it's really about making sure that you're doing it the proper way, finding that change in x over that, or that change in z over that change in x, and that change in z over that change in y, and then using a data point from your table to find that b or c intercept, whatever. So moving on, guys, we're going to look at what the slope and the intercept actually means in practical terms. So what me and Uriah came up with is the function slope in the x direction basically means that for every dollar added to the initial balance, your price after 1 month goes up by 0.07 cents. So as you can see, that positive 0.07, so that value of that payment is going up per every month. So in the y direction, it means that for every month that goes by, $8.75 is taken off the balance. And then pretty much the intercept may imply a $248.04 down payment or service fee. Perfect. So, moving on to question number 2. We pretty much wanted to use that linear formula that we found. Everybody's is maybe a little different, so bear with us as we answer this one. Your answer may not be exactly the same, but the idea is still there. We want to find the payment of an $8,000 loan at 60 months. So we're going to take these numbers and we're just going to plug and chug. We are going straight into this one. We are plugging the 8,000 into the x, plugging that 60 into the y. Again, do not mix these up. It can throw your whole answer off, giving you a number you don't want. That number we got, though, with the correct placement of our X and our Y, came out to $283.04 for that payment. So based off the table, an $8,000 loan at 60 months gives us $422.63. You could tell that our function was off by quite a bit. And so what we pretty much came up with was looking at the fact that we tried to get that most accurate fit. It can only conclude that this may not be a linear model. And looking at the table, you can kind of infer that it's not a linear model. So that could be a big reason why that number is off by as much as it is. So moving on to number 3. The question asks, when we fit a model to data, we wish to minimize the error between our model predictions and the actual data. We will not get into that here, but we will run a multivariate regression analysis. It is critical that you complete question 1, which we did, before you engage in this question. You get the satisfaction of comparing your estimates with a mathematical model. Please check out the video below. I hope you guys did as well. It's a great video. It really helps with this question a lot and a future question that we will get into. All right, so we're going to move right into Desmos. Now, what's important about this, very, very, very important, is that you are using all 25 z values from the table. So you need to plug in every x, every y, and every z value into that table into Desmos. You need that 5,012, 564, 5,024, 362, 35, 5,036, 302, 17, and so on all the way down. You cannot do 5,012, 564, 6,024. I know it's tempting to go in that diagonal just to get that average, but that is not accurate at all compared to putting every single value in and getting that perfect fit. So moving on, we're going to go into Desmos, and in Desmos you can see we have that beautiful 60 for those months, 48 for the months. It kind of cut off, but there is that 36, all the 36s, all the 24s, all the 12s, and we have all the X values as well. $5,000, $6,000, $7,000, $8,000, $9,000 for each month, and every single time it comes with that z value as well. So when we look at that formula, we have that z1 with the squiggly line from Milos's video. You can see that the statistics show a 0.81 percentile accuracy rating, which is pretty good. It's not fantastic, it's not that A status, but it's up there. And you could tell by the parameters that it gives you some quality numbers, that A, B, and C looking very good. So what we're going to do is we're going to plug those numbers into our equation, our new equation for that linear formula or function. So our new M, our new N, and our new B are going to look like this from Desmos. Then if you want to compare that to our previous model, we were somewhat close. We got kind of close with that M, kind of close with that N, and kind of close with that B. So we are pretty proud of that. So again, this question is also asking, what do the slopes and the intercepts mean in practical terms? Again, we came up with this function means that for every dollar added to the initial balance, your price after 1 month goes up by 0.07 cents. That's for the X, and then for the Y, it means that for every month that goes by, $8 is taken off the balance. So for every month you add towards that payment plan, $8 is taken off the balance. And then moving on to our intercept, that B value means that there is an initial fee of $288.01. All right, guys, so moving on to question number 4. We are pretty much duplicating what we did in question number 2, but now we're just going to be using that new, cleaner equation, that more accurate equation for that linear function. So when we plug in those numbers, $8,000 balance over 60 months, we are given $354.13. So that, compared to that 422.63, is closer, but it is also more evidence that this table is not a linear function based table. All right, guys. So moving into number 5, we want to find a close quadratic equation. Pretty much, we want to take this new equation that we were given in the discussion board, and we want to get it as close as possible to this table's values. And to do that, we got to do a little backtracking. We got to go back to college algebra. If you guys remember, there was another form of a line other than y equals mx plus b, that form being point slope form, and that form includes y minus y1 equals mx minus x1. Hopefully you guys can recall that. This form lets us plug in any set of order pairs, x1, y1, and allows us to create a starting place, even if we don't know the slope. Alright guys, so if we take that logic and we apply it to a 3D curve, we can take our starting point, the two values that give the smallest z, and put them into h and k. So guys, looking at our smallest point, you probably see that it's that 5060.264. Looks like the smallest one on this entire table. We can also plug in the z value for those two lines as the intercept, so we could plug in that z value for that c value, z value for c value. Hopefully that doesn't mess you guys up a little bit. So we take that point, 5060.264.14, and we plugged it in to this equation. It gives us a x minus 5,000 squared plus b y minus 60 squared plus that z value of 264.14. Now that we have a starting point, let's graph the curves in GeoGebra along with all 25 data points so we can evaluate the curve. It is very, very important to still use every single point in the graph on Desmos and GeoGebra to give us that best fit, guys. Keep that in mind. So moving into GeoGebra, you can see that we have not plugged in that A or that B value yet, and this is what it looks like. You can see that it is starting out at that lowest point. It is going up. I don't know if you can tell, but it kind of is. It's kind of like a curve, and this is the lowest point right here. So we can see that the numbers start at the lowest point, but but the curve itself is not following all the numbers. So you can see that it's just that little cone. So from here we start plugging in different numbers for A and B. There wasn't numbers there before, we're gonna put numbers there now. And pretty much after we plugged a few in, we sort of noticed that these numbers are gonna need to be small. And for A, it's gonna need to be really small. And for B, not as small, but still small. I'm talking smaller than 1, but bigger than 0. The A being really close to 0, that B being a little bit farther away from 0, but not really close to 1. So after playing around, tinkering with some numbers, we settled on A being that tiny number of 0.00002 and B being 0.1. So when we plug those numbers in, it shows 0 there, but it is that 0.00002. You could tell, and then that 0.1 for B. You could tell that the curve definitely stretches out, fills up the area a lot more, and kind of encapsulates all those points. Not every single point. Again, the table is not perfect. It's not going to give you a great fit every time. So you just got to play with it and mess around. But you can tell by this angle, it cuts through the majority of those points, giving us what we assume is our best available fit. There's one more angle for you guys to take a look at and analyze. Your numbers obviously may be different. It is really up to you. Whatever you feel looks the best, it is the best. Whatever is the best fit for you guys. So we came to the conclusion that these points do not fit the data perfectly, but it's close enough. So we estimated some payments, and we plugged in just a random number from the table. We picked 9,024, 652.24. So if we use that, we plug those values into our x and our y and not the z, because that's what we want to find. We want to see how close it gets to that 652.24. So when we plug those numbers in, our z value is 713.74. Now when we compare that value to that 652.24, it's not far off, but is definitely far off. It's not close. So not every time you're gonna get that perfect fit, obviously, but it's a little bit closer than that $100 difference from that linear fit. So we'll take that and we'll move on. So question number 6, it wants you to go back into Desmos, and it wants you to do exactly what you did for number 3, but instead of using that linear function, it wants you to use that paraboloid or quadratic function that we were given, that a x minus h squared b minus y squared plus c. So when we move into Desmos, and again, every single point needs to be plotted. Make sure that that is happening in the x, in the y, and in the z, so that way you get that best fit, that most accurate fit, that best answer for everybody to see. When we plug it in and we use that z1 with the squiggly to the a x minus h squared plus b y minus k squared plus c, our stats show that 0.9523 percentile, which is about 95.23%. That's much better than that 81 from that linear line. We like to see that. It shows us our numbers here. You can see that a value is tiny. You can see that b value is not as tiny. That h and that k value are something to look at, and that k value as well. When we plug it back into the formula, this is what it looks like. Again, that a value, very small. B value, not as small. The h value, it's a negative, so it's turned into a positive, x plus, because we have that x minus h. So this was a negative from Desmos, and then in here this was a positive, and then this c value is a big negative, so this was a negative value as well. So when we compare that to our original model, you can tell that we somewhat had an idea of the small a value, somewhat idea of a big, but the thing is that this one was a negative and this one was a positive, so it's kind of different. Again, not every model is perfect, except for Desmos. That's the closest you're gonna get. When you move into the y's, you could see minus 60, minus 449. So obviously they're just trying to accommodate for the best fit, and Desmos clearly is doing a better job at that. Again, neither are perfect. Desmos definitely fits better. And yeah, we will move on from there into the last question, guys. Number 7. Number 7 asks, is a linear model or quadratic model best in your opinion, and why? So looking at the data and from the questions we've already answered and what Desmos has given us for their best fit, when we compared the R2 for Desmos, the linear happened to be 0.8153, which is around 81.53%. And that quadratic came out to 0.9523, which is about 95.23%. Pretty much, this means that a quadratic model for this data set is 13.7% more accurate than the linear model. So it is pretty safe to say that the quadratic model is definitely better than the linear model. It may not be the best, but from the data that we have seen, it definitely outshines that linear function.